right, let's go ahead and get started. Angle the camera over there. Perfect. How's everybody's weekend?
Good.
Good? I didn't see who said good.
Pretty good.
Oh, good. Good, you're good. Anybody doing anything fun? Kind of hard to do anything fun in COVID world, isn't it?
Read my stats
Oh.
book.
What's that?
I said I read a lot in my stats book.
Suck up. Doesn't count. Doesn't help you. All right. All right. So what did we learn last time? We did learn about graphs. What did we learn about graphs?
Some are for nominal and polynomials, and some are for ratios, and both.
Yes, exactly. So, yeah, so Ace, we learned about histograms. So can somebody give me an example? What is a histogram? Or just kind of describe it for me. I'm sorry. Yeah, it's like a bar chart, except without spaces in between, right? And what are we depicting on a histogram? What sort of information? Yeah, frequency, exactly. Yeah, so on a histogram, let me move all of this stuff over. Crap, go back. Let's see here. Not gonna let me do it. One more time here. There we go. All right, so yes, on a histogram, we have on the y-axis, the frequency, and on the x-axis, we have our different categories. And so let's say we were coming up with a histogram for grades in this class. Let's say we have that number of A's, we'll have slightly more B's, we'll have a couple C's, and then we'll have one D and no F's. How about that? And so what this is doing is giving us the frequency within each one of these categories that we have established. Now, what's one thing you have to think about with the categories on the x-axis, both here and then other things like continuous x-axes? They're telling a story, yes, exactly. But I'm looking a little bit more to the classification. How do we decide what goes on the x-axis? Or how big we draw those groups? Depending on intervals, exactly, yeah. And so it could be the real limits, right? And so let's say we wanted to look at the actual GPA somebody has. And so a GPA average of what, like 3.3 and higher, I think is an A. Between 3.3 and 2.7 is like a B or whatever it is. And so thinking about, okay, what are those actual cutoffs and criterion for that x-axis for us to be able to establish those frequencies? All right, what's something else we learned last time? I'm sorry, one more time? My hearing is so bad. You know this from 102. Yes, stem and leaf plots, exactly. And so what is a stem and leaf plot, Sonny? Exactly. I would normally ask you to come up and draw it, but COVID times, we're trying to minimize student contact here. And so, yeah, so a stem and leaf plot, you're going to split it down the middle, And you have two columns. What goes in the left column for a stem and leaf plot? Stems, yes, exactly. So you're looking at kind of the root for that number. And so let's say we had everybody's age in this class, and let's just pretend that we have the distribution. Some of y'all are still in your teens, some are in your 20s, and then I'm an old fogey in my 30s. And so if I went around the room and asked everybody their age, maybe we would get a 19, we would get a 22, we would get an 18, we'd get a 21, then another 22, that's bad 22, and then a 20, and then we come to me and give me a 30, etc. Right? And so what you're doing is every instance of that number, you have the stem over here on the left-hand side, and you're putting that leaf on the right-hand side to indicate that here's 19, here's 18, 22, 21, 22, 20, etc. Yeah. Yeah, so if you had 100 or you had a 3-digit number, this on the left-hand side would go all the way up to 10. So you have that 10 there, which would still be that root, and then you would just have that ones place over there. Does that make sense? Perfect, of course. Good question. Any questions about that or anything else we learned last time? What we needed to know, are you talking about for the x-axis? Yeah, so you have to know what your category is. So remember last time we talked about that x-axis, if we were doing things like SAT scores, you don't really want, okay, you know, 660, 670, 680, 690, etc. Maybe you want the jumps. And so let's say if we're doing this stem and leaf plot for SAT scores, we'd say, all right, we're going to want, you know, below 700. This is going to be 700 to 800, 800 to 900, and so on. Right? So you've established those categories. You want to make it such that your x-axis doesn't get unruly, where you have, you know, 40 different categories on the x-axis. So if you can group them, it's best to do so. Other questions? Feeling good about stats already?
Can we go over interpolation?
Can we go over interpolation? Absolutely, yes. So, let me see if there's a way to clear this. Maybe not. All right, so here, give me 1 second here. All right, so interpolation is just our attempt to derive information based off of what we already know from the data we have. So let's say you went out and you ran 4 miles. All right, so you have 4 miles here. And let's say it took you 36 minutes. And you know you have 0 miles that took you 0 minutes, but you didn't measure anything in between. And so interpolation is making an assumption about the data that your progression along this course is in fact linear. So we can say, based off of knowing that you ran 4 miles in 36 minutes, that you ran 2 miles in 18 minutes. And from there, we can determine that you ran 1 mile in 9 minutes, and 3 miles in 27 minutes. And then you can get in between 2 and 3. So you ran 2.5 miles in, what was that, 4.5, 22.5 minutes, and so on. So all interpolation is doing is saying, you know, kind of this 0 point here, and you know the maximum. And so from that, you can start making assumptions about every point in the middle here. Does that help?
Yes.
Of course. Any other questions? Yes. Am I recording? Yes, I am. Thank you. Oh, no, I was just laughing. I don't know if, I think I told everybody here that if you tell me within the first 5 minutes that I'm not recording, I'll give you an extra credit point. So it doesn't count if you tell me before class starts, though. We just had that on Zoom. All right, any other questions? Going once, going twice. Sold, all right. So here's your fun fact of the day. Mr. Rogers always mentioned out loud that he was feeding his fish because a young blind viewer once asked him to do so. She wanted to know the fish were okay. It's kind of the most wholesome thing I think I've ever heard. I also like, there's a Mr. Rogers quote that I was reminded of a whole bunch at the beginning of the pandemic, where he said something along the lines of when he was a kid, he would see all these, you know, really scary things happening out in the world and on the news and stuff like that. And he said, his mom said, look for the helpers. You'll always find people who are helping in every crisis. And that really helps, I think, with that mentality of, oh my God, everything's so overwhelming right now. It's easy to not see the helpers, but look for the helpers. Life is a little bit more tolerable that way. All right, so enough of me waxing philosophical about Mr. Rogers and his sweaters. Y'all just wait till it cools down. My sweater game is strong. All right, so in general terms, we're talking about central tendency. It's just a statistical measure that determines a single value that we want to accurately describe the data, that center of the distribution. So by identifying this average score, it's going to allow researchers to condense a lot of data into kind of a single description point. Right? If I asked you to describe the age of everybody here on campus, you're probably not going to say, well, there are, 1,243 people age 18 currently, 2,915 age 20, et cetera. You're going to think about, okay, what is that average age? That just allows me to describe a college student population. Right? I think average age is 20 to 21-ish. It's allowing us to just have that descriptive, that narrative kind of description of the data itself. And then the nice thing comes in where you can compare two different groups. Right? Let's say we wanted to know, is there a difference in the ages between students at UAH and Calhoun? Right? You could think of reasons that there may or may not be differences. But by getting those average scores, we can now take a look at whether or not two different distributions, two big data sets, are similar or different. And this is a really kind of key component upon which we're going to be building everything else in this semester. Almost all of the tests I'm going to be teaching y'all this year deal with mean differences, group differences. We'll talk about things like correlations and regressions, which are more individual differences type stuff. And actually, interestingly, those are the foundations upon which machine learning and artificial intelligence are built. But most of what we're going to be talking about are just these group level differences. And so we have three commonly used techniques to describe this central tendency. I'm sure you've all heard, or at least had some peripheral experience with the three: mean, median, and mode. And so let's first go over the mean. So when you hear people say things like the average, almost every time they're referring to the mean. So the mean is just that numerical score on an interval or ratio. Now, why is it interval or ratio? Why not like nominal? Why can't we get the data or the mean on nominal data?
Because it has to be numerical.
Yeah, because it has to be numerical, right? It wouldn't make sense when you're describing the student population at UAH to take up all the men and all the women and then calculate the mean between that, because it's not representative of a student. You can't have kind of this averaging of these nominal categories. You can't get everybody's favorite color and say, okay, well, the average color based off of a numerical division of people's score is this. And so you calculate the mean by summing all of the values and then dividing by the number of scores. Conceptually, the mean is also defined as the amount that each individual receives when the total, or sum of X. Again, what is this sigma? Sum? Exactly, yes. So when you see sigma X, that means take every X value, every data point, and add them together. And then you're dividing equally amongst, or by big N. And what does big N signify?
Sum of those scores in a population. I mean, not sum of, sorry, scores in a population.
Exactly, yeah, the number of scores in that population. And that mean is just the balance point of the distribution. And I'll show you a representation of that in just a second. So we can also think about the mean. I mean, if we are just taking these two notations here and writing sum of X over N, right? That's the mean. So if you see this in various equations, just know that all this is telling you is get the mean. Once we start adding letters, I think people get a little nervous. And so just understand you can break down each one of these subcomponents into something very tolerable. So when I say the balance point, I literally mean if you were to put equal weighted blocks along a continuum at these different points, the mean is the exact point at which that seesaw would stay balanced. Right? So if I have 2 2s, 1 6, wow, that's awful handwriting, and 1 10, add them all together, that's 4, 10, 20. 20 divided by 4 is 5. That's that mean. And again, if this were in the real world, it would literally just be balancing there. And so I showed you kind of alphanumerically how we depict mean. So sum of x, sigma x over big N. But this lowercase, what looks like a u, is our mean. All right, and so if we say in this case that just means the mean, the measure of central tendency gives us 5. Question so far? Yeah. What's the difference between mu and what? M. So in the same way that we have kind of lowercase notation and big notation for n, that means the same thing. The lowercase mu is representative of the sample mean, and then big M is usually denoting the population mean. But you'll see it a lot in papers where people write big M and SD, because within APA formatting, it gets a little squirrely and unruly in that when you're actually writing it out, frequently people just write M equals, which would be the same thing. Yep, good question. Other questions? Yeah.
I think you mentioned it backward to what it was in the book. So in the book, it says that the mu is for population, actually. And that the
Did I say mu is for sample?
Yeah.
Yes. Sorry.
Okay.
Yeah. Thank you for catching that. All right, because the calculation of the mean involves every single score in that distribution, changing the value of any score is going to change that mean value. To determine how the mean will be affected for any specific situation, you have to first figure out the number of scores. How many of those are affected? How the number itself is affected? And then how the sum of all of those scores is affected. All right, so real quick practice. Go ahead and find the mean of these numbers here. Then add 3 to each number. Recalculate the mean. And then don't worry about the subtract 5. So everybody practice that real quick, and then we'll bring it back together. Way to go, Jay. That was fast. Who still needs more time? Cool. All right. So what is the mean for all of those numbers? Just the outright mean. Yep, I'm seeing it on Zoom, 32.5, right? All right. And then when you subtract 3 from every score, what does it mean? Or excuse me, when you add 3. Did I get it? 35.5, yep. So if you do something to every point, you're also doing that to the mean, right? So if you add 3 to every point, you're also adding 3 to the mean. Cool? I think it just helps to conceptualize what changing various numbers will do to your measure of the mean. So yeah, so you have your mean of 32.5, add 3, you get that 35.5. Subtract 5 from the original, you get 27.5. Pretty straightforward. Like I said, if a constant value is added to every score in the distribution, then that same constant value is added to the mean. Now go ahead and do this real quick. So find the mean, and then multiply every score by 5, and recalculate the mean. Jay and Apollonia killing it over there. Mighty quick. All right, so we've got the answer on Zoom here. What happens to the mean once you multiply everything by 5? Yeah, exactly. You just multiply the mean by 5 if you're doing it to every individual data point. So again, this should help kind of crystallize in your mind the relationship between the mean and changing amounts for each one of the data points. So whatever you do to every data point, you have to do it to every data point, but what you do to every data point, you subsequently also are doing to the mean. So if we get 2.75 as our original mean, once we multiply that constant by the mean, we get that 13.75. So if, for example, hint, hint, I were to give you a question on the exam that said, here are 50 numbers. Here's the mean for those 50 numbers. Now multiply every number by 2.3. What's the new mean? Yes. Yeah, exactly. Sorry, I can't tell who's talking, and so if I'm not looking at you when you're talking, I think it came from this general area. But yeah, you just multiply it by 2.3, right? Don't spend the time doing all that extra work. Make it real easy on yourself. Yep, just what I said. So we frequently use the mean. And I already talked about one instance where the mean won't work, right? When you're using nominal or ordinal data. But you also don't want to use the mean if you have real extreme scores. Right? We talked about when data is skewed last time. What would a positive skew data set look like? Yeah, so you get kind of a grouping at the lower values. And so a positive skew data set would look like this, right? So you get a big clustering down here, but then you've got this tail where you've got a few outliers. And so in this case, if we have this data set, this positively skewed data set, you're probably going to have a mean somewhere out here. But that's not really representative of all the data, right? You just have a couple extreme outliers that are skewing the data. So let's look at these scores here. Let's say we have the salaries for a whole bunch of recent psychology graduates from UAH, and we get every one of their scores, or excuse me, every one of their salaries, and we count the number of people that have that salary, and then we calculate the mean, right? Means $47,000 that people are making. But let's say now we take 24 of those 25 people, and we had somebody who just hit it big, had a big startup idea, and now made $1 million in their first year after graduating. Well, you can see that mean went from 47,000 to almost 85,000 based off of one specific score, right? So you can see how the data set didn't really change, but for one person. But that score that we're expecting to be completely representative, that mean, is no longer really all that representative. In fact, there's only one person that makes anywhere north of 84,000, 85,000. So in the mid-1980s at the University of North Carolina, the average starting salary of a geography major graduate was over $100,000. Any idea why? Yes. Do you know who that outlier was? It was Michael Jordan, right? And so Michael Jordan was a geography major at UNC. He graduated. He clearly wasn't using geography, but he was getting paid exorbitant sums of money, which bumped up UNC's geography major starting salary, right? And so if you are UNC, now you can say, come join our major. Our majors average $100,000 per year. That's kind of false advertising, right? You're not really averaging $100,000. Michael Jordan's averaging a couple million, and everybody else is averaging, I don't know, 45,000 a year. All right, so you can start to get a good idea why you may not want to use that mean. So like I said earlier, with data from a nominal scale, it's going to be impossible to compute that mean. All right, if we ask people what their favorite fast food restaurant was, you can't find the average between Taco Bell, McDonald's, Wendy's, Burger King, Chick-fil-A, etc. Right? The average just doesn't make sense in that case. And when you're using data on an ordinal scale, it's usually not appropriate. What's an ordinal scale? Yeah, exactly. So ordinal scale is just ordered ranks, right? Like you get with a race. It doesn't make sense to average those actual positions. Now, sometimes you will see people say, you know, on average, so-and-so came in, 3.5th place. First off, that doesn't mean anything. You can't come in half of a place. But it also doesn't give you really all that good of an understanding about how close they were to any of these other positions. Maybe they came in first every time, except for the one time they came in 200th. Right? Again, that isn't really a reasonable description. So when calculating the median, we are taking literally the middle score. So we're going to arrange our scores from smallest to largest. And the median is just that middle point on that list. And the nice thing about the median is exactly 50% of people have scores below that median, and exactly 50% are above that median. So whereas with this example before, only 4% of people had a score above that mean, 96% had below. When we get to the median, it will be a 50-50 split. And this is why you'll see a lot of descriptors like median family household income, right? Not mean family household income. Because you're going to have people like the Jeff Bezoses of the world, who I think is on track to become the world's first trillionaire by 2035 or something like that. But that's not really a good descriptor, right? We want the median family household income. I don't know why I struggle saying that. So you know that half of the people in that data set make more than that amount of money, and half make lower. So usually we just find the median by a simple counting procedure. So with an odd number of scores, you list them smallest to largest, and the middle score in that list is the median. And so if, let's say we have 2, 3, 5, 7, 9, 5 is our median. If, however, we have an even number, so let's add 10 on top of that, we are taking the mean of the middle two values, right? So in this case, the middle two values are 5 and 7. We take the mean, and so in this case, the median would be 6. So even though 6 doesn't appear in that list, that is our median because of how we calculate it. So again, representing this here, you have an odd number up top, 5, you count in 3, because that's going to be that middle point. That gives you a median of 8. Down below, You have an even number, so between 4 and 5. So your median point will just be 4.5. Questions about this so far? This is probably a refresher for most of y'all. Awesome. So now let's go back to our earlier salary example. Our median in this case is 48,000. And if we add that $1 million earner in there, we add the Michael Jordan of our data set, that median doesn't change, right? And so you can think about the median being fairly robust to these sorts of outliers. It would be a lot more representative if the UNC geology department decided that they were going to report the median salary than the mean salary. So on average, the median is going to be relatively unaffected by those extreme scores. Thus, that median tends to stay in the center of the distribution, even when you do have some extreme outliers. So who can think of other real world examples where we may want to take the median instead of the mean? Yeah.
Like you said earlier, we're going to pick the arrow page in the group, right?
Easy there, smart Alec. I'm kidding. Yes. So if we took everybody's age in here, I'm going to throw it off a little bit, right? So now instead of the average age being, I don't know, 21, because I'm in this data set, the mean age would now be 23 and a half, right? And in reality, there's only one old fogey who's throwing it off. So if we took the median, I could be 100,000 years old and not affect that central tendency point. I'm kidding. I called myself old. Oh, but don't worry about that. At some point, y'all will hit 30 and you'll have an existential crisis where you have to rectify the fact. In my mind, I'm as old as all of y'all. And then I hit 30, I'm like, no, I'm an old man. I have to start watching my fiber intake and going to the early bird specials at Denny's. Kenya says, when you have an undetermined score. So yeah, if you have an undetermined score, I mean, it kind of depends on the setting. She says, taking data from a set of people taking a test and one person doesn't finish the test. Yeah, and so in that case, let's say if you don't finish the test and you don't hit submit on the test, you get a 0. Well, that's not really representative of the average class score. And so that median would be a little bit more representative. The problem is it can be so immune to extreme scores that it may not give an appropriate understanding of reality. So let's say we took all of your salaries during the school year, and half of you weren't working, and the other half were. We could get a mean that would be between 0 and whatever that average salary is that y'all are making. Or if we have the median, it may be the case that the median is $0, right? And that wouldn't provide a good indication that half of the class is working during the school year. Or conversely, it could be, that the median is up at, let's say $10 an hour. That doesn't give an indication that in reality, half the class is not currently working or not currently earning a living. So you can see how there are trade-offs. Sometimes it's good to have that robust immunity to those extreme scores, but it does also sometimes cloud the actual picture of the data. The final measure of central tendency that we're going to talk about is the mode. And the mode is just the most frequently or commonly occurring category or score, or even anything on the continuous scale in that distribution. And when you do a frequency distribution like we did last week, so you have a histogram, that mode is just going to be the highest point. So if we have our distribution here, the mode is going to be that point where it tops out. The nice thing about the mode is you can use it for any scale of measurement. All right, and so if I polled everybody in here about their favorite college football team, you can't really have a mean favorite college football team. You also can't have a median because there's no way to rank it from smallest to biggest. But we can get the mode, right? So in so doing, we can figure out that the average, as determined by the mode, favorite college football team would be Auburn, right? Side note, did y'all see that Auburn has 9 confirmed coronavirus cases on their football team? I don't want to get conspiratorial, but I think Nick Saban came and infected the locker room for Auburn. Just a rumor that I'm starting. Although this is recorded, so for legal reasons, I think I have to say that's not true. All right. So the primary value of the mode is that it's the only measure of central tendency that can be used for data measured on the nominal scale. Right, like we just said. And so I think last week I made mention of what's known as a bimodal distribution. And like the name would suggest, bi meaning two, modal meaning modes, a bimodal distribution has 2 modes. So we can say that distribution, if those modes are not equal in stature, I'll show you that in just a second. One can be a major mode, and another can be the minor mode. And so if we look here, it wouldn't necessarily be all that representative of the data to say the mode is 2, right? Because even though this is the highest point, it really kind of neglects the fact that there is another kind of distribution occurring at the high end of the scale. right? And so we go back to this whole idea of narrative, right? What is the story we're trying to tell? It may make sense to say this is a bimodal distribution with the major mode at 2 and the minor mode at 10. Who can think of other real-world examples that may be a bimodal distribution? Yeah. Mm-hmm.
It affects young people, like really young people, and really old people.
Yes. Yeah, exactly. And so you can look at the number of cases. You would likely have a lot of cases for really young children, right? The flu can be really deadly for young kids. And then it doesn't really affect those, like, I don't know what the age is, but from 10 to 50. But then when you start getting above 50, it starts disproportionately affecting the older generation as well. And so it wouldn't make sense to just say that the flu only affects those who are old or only affects those who are young. You want to have a representation of that mode that says both the young and the old. It also, that's a great example because it wouldn't make sense to say, okay, what is the mean age of somebody affected? Well, if you took all the really young people and all the really old people, you may get a mean of 35. Well, that doesn't make sense because 35-year-olds aren't really affected by the flu. At least that's what I have to tell my old self. It also wouldn't make sense to do the median for the same reason, right? So you want to think about, okay, what is the best representation of this actual data? Age of students upon graduating college. Yeah, so you're going to have probably a major mode right around the 22, 23, 24 age. But then you may also have a secondary mode of, professionals who have already, started their family and kids are now off in school. And so maybe you get a secondary mode of around 40 or so. Great. Because the mean, median, and mode are all measuring central tendency, they all systematically relate to one another. So when a distribution is a symmetrical distribution, right? Think about those normal bell curves. The mean and median and mode will always be the exact same value. All right, so if we draw our, let's assume that's perfectly symmetrical. Your mean is going to be right in the middle. Your mode is also going to be right in the middle because that's the highest point. And your median is going to be right in the middle because you have an equal number of people on both sides. In a skewed distribution, on the other hand, that mode is going to be at the peak on one side. The mean will usually be displaced towards the tail on the other side. And then that median is usually in between the mean and the mode. just representing this graphically. Again, you have a positively skewed distribution. Your mode is going to be at the peak of that distribution, right? Because this is just a frequency graph. Your mean is going to be skewed by these outliers, the Michael Jordans. And then your median is similarly going to be skewed by the fact that there's a little bit more weighting over here. Not weighting in terms of like the extreme score, but weighting in the sense that there are more people in this kind of drawn out area than there are over here. The flip side, you have a negatively skewed distribution, mode right there in the middle, mean affected over here, and then the median in the middle. All right, so somebody give me another example of when we might want to use the mean. What sort of data? What real world example would we want to use the mean for? Average what? Average in time, you said? Yeah, exactly. So let's say we were looking at how fast you could run miles, right? We would then have an average in seconds, where mean would probably make a lot of sense. What about median? What's another real world example where we would want to use the median? What's something that would have a real extreme, either high or low score? Looking for data for an extremely rare disease. Yeah, and so I'm trying to think of practically what that would look like. But yeah, anytime you've got a extremely non-representative data point, you're going to want to use the median. So let's say I wanted to look at the average number of donuts I eat a year. Well, 300 plus days a year, I eat no donuts. But when I get donuts, I have no self-control. And so it could be like this weekend where I had 8 donuts over the course of 24 hours. And that kind of distorts it to make it look like I have, you know, a quarter of a donut every day, when in reality, most of the days I'm really responsible. But some days I go off the deep end. Yeah, Amanda also says median household incomes of a large city such as Nashville. Absolutely. Yeah, anytime you're talking about income, usually median is going to be the best way of calculating. And then finally, somebody give me another example of mode. When would we want to use the mode? Give me a real world example. Yeah, people's favorite colors. Exactly. You can't find the mean favorite color. Can't find the median favorite color. Yes, Kenya says favorite TV show. Exactly. The mode for that one should be The Office. All right, questions about what we covered today? concerns? Everybody feeling pretty good so far? Cool. I'm going to try to do checks with y'all throughout the semester. We're going to start ramping it up on Wednesday. So everything we've talked about up to this point has probably been largely a refresher, but we're going to start getting into variability and variance on Wednesday. And then we'll start picking up a little bit more of the computation and calculation. So make sure that you are squared away and ready to go on these concepts. If you have any other questions, I'll happily hang out for a little bit. We're ending class a little bit early. Otherwise, I will see y'all in person next Monday and Zoomies on Wednesday. Just kidding. Monday's Labor Day. I won't see y'all on Monday. Don't come to class. I'm not going to be here. Thank you, Apollonia. If you have a bimodal distribution, can you have 2+ modes? Yeah, Skylar. And so that's what I was talking about with the major and minor modes. And so the major mode is going to be the essentially highest peak, and then the minor is going to be that other mode, but that is slightly less. Amber says, my power went out. I just got the last bit of what you said about make sure we know. No, there's no quiz coming up. That was just information of you will likely be quizzed on that. And so just make sure that, I think that was in relation to knowing if you do something fixed to all the numbers in a distribution, it happens to the actual mean itself. William says, for the exam, will things like the book that we don't go over much in class pop up? Not really. Most of what we cover will be in class, between in class and in the lab. That'll be most of what you need. The last week's lab quiz, is there any way I can see the correct answers, how they were calculated? I missed all the calculation questions, I'm not sure. Yes. So email the TA, Caitlin Davis, and she can go over all of those with you.